All right. Yeah, thanks for coming after this difficult night. And yeah, thanks a lot for the organization of this fantastic conference. Somehow when I signed up to speak here, I expected this to be a much more low-key event, but it turned out to be a major conference. I think it's testament to the abilities of the organizers, and yeah, thanks for inviting me to speak here. Yeah, so we heard a lot about evaluation theory this week, and okay, what I want to talk about is maybe a slightly curious application of evaluation theoretic methods in analysis. Okay, now I'm not sure how interesting this is to actual analysts. I mean, for them, this is maybe baby analysis, but still I think it's interesting because it's sort of a coherent theory and certain kind of classical theorems that one knows from analysis suddenly have a, I don't know, an algebraic framework that somehow explains them. Okay, so yeah, this is all joint work with Lau van Andries and Joris van der Hoeven, and we recently put a manuscript on the archive with the title Maximal Hardy Fields. And yeah, this is not supposed to be definite. I mean, it's mainly for people to read, but somehow we're still not quite sure how to publish it and what to add and subtract from it. And this is a fairly comprehensive study of algebraic systems of algebraic differential equations, also involving asymptotic side conditions over so-called Hardy fields, which I'll introduce later. So in a nutshell, Hardy fields can be seen as sort of a natural domain for a part of asymptotic analysis that you can treat algebraically, right? Of course, in asymptotic analysis, the main difficulty that you have to deal with is oscillation. So in the Hardy field context, this oscillating phenomena are somehow excluded by definition. But as we'll see later, we do have some tools to allow mild kind of oscillation phenomena. And one can see them as sort of, I don't know, the poor one-dimensional cousins of O-minimal structures. So it's a purely one variable theory. I'll talk maybe a little bit about the connection to O-minimality later when we talk about examples. And yeah, they have a lot of applications, mainly in dynamical systems in the work of Écaille, although it's maybe not explicit there, but really the techniques that underlie everything there are of the Hardy field nature. But it's also interesting, they are used in ergodic theory. So I don't really know much about these applications, but I just thought I would name drop some people who worked on this subject. It started with Burschen-Nitzan. And so, for example, if you look at semi-radius theorem for the existence of arithmetic progressions, if you replace the multiplication function by some other function that lives in a Hardy field, they try to prove theorems about the existence of long, I don't know what to call them, Hardy progressions, and somehow this works under certain assumptions. Okay, yeah, so as I said before, the main focus there in this whole business is on arbitrary algebraic differential equations, arbitrary number of variables, arbitrary degree and order. But what is interesting, and this is what I want to talk about today, some people here might have heard my talk last year at Leeds. So today I want to place a little bit a different focus, namely that this also gives interesting information just about the basic case of linear differential equations. And you probably have to go through this whole theory to get these results. So I think that's interesting. And yeah, so the plan for the talk is that first I'll introduce Hardy fields for those who haven't heard me talk about this before. So for those who've heard it, this will sound familiar. Then I'll state our main theorem, but I won't really go much into the detail about even the proof. But then I want to focus on the applications to linear differential equations. And they mainly come in, well, there will be mainly three parts. First, I'll talk about the parameterization of solution spaces. Then about the factorization of linear differential operators, which is closely connected to that. And then at the end, I'll focus on the special case of order 2, which is quite important for applications in, mathematical physics and all kinds of applied fields. Okay, so first Hardy fields. Okay, so I need some notation. So we first introduce, for every natural number r, the ring C to the r. So this is the ring of terms of r times continuously differentiable functions defined on half-lines going to plus infinity, where the half-line is allowed to vary. And terms, two such functions on such half-lines are said to be equivalent if on some possibly smaller half-line they agree. So this defines an equivalence relation, and the quotient gives you this ring of terms. And then if you take the intersection of all these C to the r's, you get the ring that we denote by C to the less than infinity. So this is, everybody in this ring for every r has a representative that is an r times continuously differentiable function. But the r, as you increase the r, the half-line might shrink. Okay. But this is, in a natural way, a differential ring, because you can define the derivative pointwise, right, on representatives. And it has, of course, subrings, differential subrings, namely C to the infinity and C to the omega. And those are given by, those are those terms which have the representative that is actually C infinity on the whole half-line, or actually analytic. Okay. And then the definition of what a Hardy field is that it's simply a differential subfield of this first ring, C to the less than infinity. And the emphasis is, it maybe should be on differential and on field. Okay. So it's close to taking the derivatives, but it's also supposed to be a field. And now, of course, you can, in a similar way, do the same definition by replacing C less than infinity by C infinity and C omega. So you define C infinity Hardy fields and analytic Hardy fields in the same way. Okay. Okay, simple examples of analytic Hardy fields. Well, any constant term lives in C less than infinity. And so in particular Q, right, identified with the terms of the constant functions, is closed under taking the derivative. That's a stupid kind of Hardy field. You can also take the reals, but maybe more interesting, you can take the term of the identity function x, right, and look at the terms of rational functions over the reals, and that defines a Hardy field. Why? Because, if you look at the numerator of your rational function, it is eventually of constant non-zero sign, so it makes sense to look at quotients of polynomials, and it's obviously closed undertaking the derivative. And then you can play a similar game by also joining e to the x, for example, or log x. Right? You can build successively larger Hardy fields. Okay, now this seems like a very simple definition, but it has a lot of quite strong consequences about the behavior of these terms that can live in a Hardy field. So let's take a Hardy field H and the term f in there. Then if f is not 0, then because H is a field, it has to have a multiplicative inverse, right? So 1 over f has to live in H. And that means that the function f, because it's also a term of a continuous function, has to eventually be either positive or eventually be either negative, right? So this also means in particular that you cannot have infinite oscillation of the functions in your Hardy field. They have to decide on a sign. Okay, but consequently, this means that you can define an ordering on the Hardy field by simply declaring terms to be positive if they have a representative that is eventually positive. And this makes H into an ordered field, right, in the sense of algebra. Okay, now you can also play the same game that we just played with, instead of f, with the derivative of f, because the derivative of f is also supposed to be in H. So if it's not 0, its sign has to be either always bigger than 0 or always negative. So this means that the function f, or I keep mixing up the terms and the functions. The term f is eventually monotonic, right? So it's because of the behavior of the derivative. So this means the limit as t goes to infinity of f of t has to exist in the extended real line. Okay, now there's a little bit more structure. Every Hardy field comes with essentially evaluation, but I prefer to talk about it in terms of what we call the dominance relation. And well, this can actually be defined in a more general context. Since I'll need this, I'll do it right away in a more general context. So let's say instead of Hardy field, you have any ordered differential field. So I have no interaction among the ordering and the derivation. We have always the field of constants. So in the Hardy field case, that's just a subfield of the reals. And then for f and g in H, we define f to be dominated by g if f is capital O of g, right? So it's bounded by some positive, f is bounded by some positive constant in absolute value. And we can also define the strict dominance relation, f is little O of g, in a similar way. Okay, now, here are some examples. Of course, lots of the limit behaviors of these various functions here that we know from calculus, we can write down now using the dominance relation. So, for example, the logarithm goes slower than e to the x, and e to the x goes slower than e to the 2x, and so on. Now, for this audience, I don't need to really say this, but it's clear that this is closely connected to evaluation theory because if you look at all those elements which are bounded by 1 in this dominance relation, then this is nothing but the convex hull of the constant field in C, as a constant field C in H, and this is a evaluation ring, as it turns out, and its maximal ideal is precisely those elements which are little o of 1, right? So I write the maximal ideal not with m, but with little o. Okay, so here are some examples of functions in Hardy fields, and it sometimes takes a bit to prove that they live in Hardy fields. So, for example, the arrow function, right? And you can see the behavior, right? As you go to plus infinity, it's nicely behaved. But also, if you look at these two, this linear differential equation x double prime minus xy equals 0 has two distinguished solutions, which are called the Airy and B-Airy function, and they also live in the Hardy field. But of course, you might say, oh, wait, there's this oscillation here. But of course, that's going to minus infinity. If you look at the behavior at plus infinity, it's nice and monotonic. And then the third example is of a different nature. So this is the gamma function. Again, on the negative half-axis, it has this all these asymptotes. But on the positive half-axis, it's nicely behaved. And it generates a Hardy field. This is not so obvious, and the example is different because the gamma function does not satisfy a non-trivial algebraic differential equation over the constants, whereas these other functions up there do. Okay, more examples. So this comes, the terminology Hardy field comes from Hardy, who constructed a Hardy field, which he called the field of logarithmic exponential functions. So he started from the constants and x, and then kept closing off under the arithmetic operations, exponentiation, logarithm, and composition. And he essentially showed that what you get is a Hardy field. So here are some examples of these logarithmic exponential functions. For example, the hyperbolic sign would be an example. Okay. Yeah, and then I mentioned O-minimality before. So every O-minimal structure, O-minimal expansion of the ordered real field gives rise to a Hardy field by looking at the terms of the definable functions in one variable. And this is essentially a consequence of the smooth monotonicity theorem. Okay, and for example, for the ordered field R itself, what you get is all those terms of continuous functions which are algebraic over the rational functions. So that would be the description of the Hardy field associated to that basic O-minimal structure. So there's of course, we have a lot of examples of O-minimal structures, so there is a lot of supply of interesting Hardy fields. But still, you can sort of take a more abstract point of view, right? You have, let's say, an algebraic differential equation of the form p y y prime dot 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 y to the r equals 0. where the coefficients come from a given Hardy field, so H is a Hardy field, then can you find a solution in some Hardy field extension of H to this differential equation? So there's lots of the examples of this kind proved over the decades. Starting actually with Hausdorff, he didn't work with the derivation, but he asked similar kind of questions for fields that are just subfields of the ring of continuous functions. And then, of course, starting with Hardy and Bourbaki and later Rosenlicht and Boschanitsan, who did a lot of work. So, for example, one thing that these people showed is that the first, the simplest kind of linear differential equation, y prime plus fy equals g, if f and g are in H, well, okay, we know this linear differential equation has solutions, right? But every one of these solutions is actually contained in a Hardy field extension over a given Hardy field H. So in particular, you can always integrate, right? So if f is 0, then you just talk about the antiderivatives of g. Also, the case where both f and g are 0 is interesting, because this means you can always join constants to your Hardy field, right? So yeah, you can always join every real number. You can also always join the term of the identity, because that's x prime equals 1. And you can integrate, exponentiate, and take logarithms. Okay, now, so of course, if you iterate this procedure, then essentially what you proved is a general version of this theorem of Hardy, namely that the field of LE functions, starting not from the constants, but from some other Hardy field H, produces a bigger Hardy field closed under x blog, etc. Okay, so now you can take this to an extreme and say, okay, well, maybe it's conceptually easier to just imagine that we have if enlarged the Hardy field so big that it's maximal. We cannot make it bigger. By Zorn's lemma, we can always do this. And then these previous results, well, there's one result I didn't mention, namely closure under algebraic equations. But in a nutshell, this result on the previous slide tells you that every maximal Hardy field has to contain all the real constants. It has to be real closed under integration, exponentiation, and logarithm. So what more can you say? Well, okay, the next level of difficulty is the order 2 equations. But of course, there the trouble already starts, because that's when the oscillation keeps creeping in. So you cannot expect a result like the order 1 equation that we had before. So, in fact, things are even worse. I mean, well, sometimes if you have a non-zero homogeneous, a non-homogeneous order 2 equation, you can solve it in Hardy field. In fact, the equation y double prime plus y equals e to the x squared. Well, the solutions, if you have a particular solution, is an affine space over that generated by sine and cosine. But any one of these generates a Hardy field. So this was shown by Boschanitsan. And this immediately tells you, of course, that if you have any two different ones, they cannot lie in the same Hardy field, because then I could subtract and I would get sine and cosine. So this means you get at least continue many different maximal Hardy fields. And in fact, you can show that there are 2 to the continuum many, which is the maximum number. But that takes more work. Okay, but on the other hand, there are some order 2 equations that do have Hardy field solutions. Well, we mentioned the Airy equation before, but here's another one that I like. This is I think it's called the Cauchy-Euler equation. So here, the coefficients are actually just real numbers, multiplied with x inverse and x to the minus 2. And there you can tell when you have a Hardy field solution in terms of a algebraic condition on these coefficients c and d. Okay, so for those of us who teach calculus, we know how to solve this, and if you're bored, you can do it now. Maybe later I'll do it if I have more time, because this example will come back. All right. But this is one of the cases where you can actually explicitly solve the equation, which of course, as we know also from ODE theory, is not always the case. Yeah. All right, so now our main theorem. And yeah, I like to phrase this as a sort of a transfer principle for maximal Hardy fields. So we now want to view these Hardy fields as model theoretic structures. And the language that we use has the following primitives. So first, it's the language of differential fields. I use this for the derivation. There's a symbol for the ordering, and I also want to throw in a symbol for the dominance relation. Okay, so both, in the maximal Hardy field context, the ordering is definable from the differential field structure because maximal Hardy fields, remember, are real closed. And the dominance relation is also definable because it's the convex half, it's given by essentially by the convex half of the constant field. But it's useful to have them in the language. And the theorem then is that any two maximal Hardy fields are actually elementarily equivalent in this language, so they're indistinguishable from the point of view of first order logic. Okay, so now we have, of course, the way that we prove this is using more precise results as a consequence of more precise results. The common theory of these maximal Hardy fields is in fact model complete. And for this, we actually need the inclusion of the dominance relation. This is not true if you leave it out. And if you allow yourself to expand your language slightly, essentially just by two convex subsets, then you get quantifier elimination. But as I said, I don't want to really get into the details here. But the consequence of this is that you have substructure completeness, right? So now if you have any two maximal Hardy fields and you have a common Hardy subfield, well, then you can actually check that in this expanded language, these are extensions. So by substructure completeness, this actually gives you elementary equivalence over a common Hardy subfield, which also will show up at some point later. Okay, and you can similarly play the same game with C infinity maximal Hardy fields and C omega maximal Hardy fields. And in fact, the theories that you get will be the same. So for model completeness, for example, you get some sort of approximation statement that if you have let's say an analytic Hardy field, right, and you have an algebraic differential equation which has a solution, some bigger Hardy field, then by model completeness, it actually has to have a solution in this, an analytic solution living in this maximal C omega Hardy field. Oops. Okay, yeah, so one slide, or maybe two slides about the proof. So the key is to show that, well, the key was that we already knew what the theory was supposed to be. Okay, so we showed that this is elementarily, every maximal Hardy field is elementarily equivalent to the value of the differential field of the so-called trend series. Now these trend series are formal series. Often they are divergent, and they can be pretty complicated. I mean, they're built up not just using the powers of x, but also exponential and logarithmic terms. So there's a certain inductive construction, and they can be used to model the asymptotic behavior of germs in Hardy fields. So rather than giving you the definition, I'll just give you some asymptotic expansions of these functions that we saw before, and I think you might be convinced. So for example, the arrow function, there's a classical asymptotic expansion, right, which is essentially here some series next to the -1. And then there's another term here, an exponential term. And in the trend series, this is simply considered to be another monomial. And then there's a similar expansion for the Airy function, which is a bit more complicated, right? So it's phrased here using this change of variables. So it's written in terms of psi. And then, of course, there's the famous Stirling expansion for the gamma function. And well, it's in fact for the logarithm of the gamma function. And if you read it, it's again the right-hand side is a trend series. It involves a logarithmic term. And in the trend series, you can take exponent logs, right? So you could take the exp of both sides here, and you would get something for somehow representing the gamma function rather than just a log. Okay. Right. So these trend series they form an ordered valued differential field, So there's a dominance relation on them as well, defined in the same way as before. And a couple years ago, we isolated a set of axioms for this complete theory of this beast. And we called the models of this the age-closed fields. Okay, and so these axioms, okay, I don't want to give them, but basically they come in a bunch of groups. So the first, the axioms for so-called H fields. So those are very basic. They basically contain information like you have an ordered differential field. The dominance relation is given using the convex half the constant field. There's a certain interaction between ordering and the derivation. Then there's another set of axioms which express that this H field is Liouville closed, which essentially says that you're closed under X band log and integration and real closed. So in some sense, this deals with order 1 equations, order 1 linear differential equations and algebraic equations. Then there's another axiom which is slightly mysterious. So this is the omega freeness. This tells you which order 2 linear differential equations have solutions. And finally, there's a property which we call Newtonian, which is, if you want to see the analogy to model theory of valued fields, is analogous to the Henselian axiom. But it's a bit complicated to define, so I'll not do it in this talk. Okay. Right, and the arguments involved are purely algebraic and use, of course, valuation theoretic tools a lot, PC sequences, Newton diagrams, and things like this, immediate extensions. Okay, now once we knew these axioms, there was actually an earlier theorem of van der Hoeven where he constructed essentially a model of these axioms, which was a Hardy field and could be embedded into T. Now this, of course, gave us hope that all maximal Hardy fields are actually H-closed. And well, then the job was just to show that this is the case, okay? All right, but first we thought that this was just a matter of doing some analysis. I mean, you have to verify these axioms. For example, this Newtonian axiom postulates the existence of certain solutions, right? But it was more complicated than that. I mean, we needed to also develop the tools that we needed for the first theorem to get the solutions to get the equations into a shape where we can actually solve them in analysis. Martin had a question.
Do we all embed into T?
No, I mean, no. I mean, the maximal Hardy fields are much, much bigger. Yeah. Yes, yeah. They will contain trans-exponential elements, and yeah. Say again? That element, yes, an element. Okay, but okay, so there's a whole algebraic part, but there is also some analysis involved. So you need, okay, as I said, you need to solve certain kinds of equations. That's what the Newtonian part says, and that, of course, you set up using fixed point theorems, etc. But maybe a little bit more surprising was that we also needed results about exponential sums, uniform distribution mod 1, and things like this. And on the next slide, you will see why. Because, well, there's a certain inductive process, and inductively, we needed to understand the solutions to the linear differential equations first before we could tackle the next inductive step. And well, this is a little bit like in Henselian axiom, right? I mean, you look at solutions of the linear part and then try to lift them. And this is something that's going on here. And so, of course, here the linear part is more complicated. It's a linear operator, differential operator. Okay, so the upshot is that we needed a detailed description of these solution spaces of linear differential equations, not just over K, but actually, not just over H, but also over its complexification K. And I think this is of independent interest. Okay, so this is the fundamental theorem. So suppose you have a maximal Hardy field, and you have a matrix, n cross m matrix, with coefficients in this complexification. And you look at the differential equation y prime equals m times y. So we know again from calculus, we know that this is a an n-dimensional C vector space, right? So it has a basis. And the theorem says that there's a very explicit basis that you can choose. Namely, the terms look like f1 times e to the phi1i, f2 e to the phi2i, etc., where these f's are column vectors in K, so they don't oscillate. And of course, this e to the phi I, well, these guys are oscillating, but the phase functions, or frequencies, if you like, are actually from H. So the oscillation is not too bad. And yeah, I said here, this generalizes a fundamental theorem about so-called holonomic functions. So that's a special case where K is just the rational functions over in X over the complex numbers. So there's a similar kind of description, and this is a generalization of that. Okay, so one should think of these phase functions, or maybe they're derivatives, or actually, to be even more precise, they're cosets modulo the group of logarithmic derivatives of K as some sort of eigenvalues of this system. So we define a notion of spectrum of a system of linear differential equations, and there's some, a little bit of algebraic theory about these eigenvalues. And yeah, and you can make this theorem a little bit stronger. I mean, you can, for example, make sure that there's no interference among these eigenvalues in the following sense, that you can arrange that either these phis are 0, or they go to plus or minus infinity, and any two of them are either identically equal or they go far apart, right? So the difference is goes to plus or minus infinity. And then for a fixed j, if you look at those fi where phi I is phi j, you can make sure that these guys are actually valuation independent. Yeah, so I mentioned that there's a little bit of algebraic theory around these eigenvalues and this computation of this spectrum. So if your matrix has some sort of symmetries, algebraic symmetries, then this can be, you see that this is reflected in the structure of the spectrum, and this allows you to predict something about the solutions. So for example, yeah, I mentioned one example here. So for example, if M is skew symmetric and the n is odd, then it actually turns out that you have to have an eigenvalue 0, and this means that you have one column vector as a solution which is non-oscillating. Yeah. Yes, question?
What do you mean by valuation independence?
Well, I mean, you just, on k to the n, you take the maximum valuation, right, and yeah, as a valuation basis. Yeah, there's in the sense of valuation independence. Yeah, because the f's they live in k to the n, right? So there's the dominant relation extended to k to the n. Okay, right. Let me give you a fun example, okay, of this business about skew-symmetric matrices, and these are the Frenet-Serre formulas from elementary differential geometry. So if you have a C-infinity curve parameterized by arc length, then, well, there are two parameters associated with that, which is first the tangent vector, right, gamma prime, and the curvature. And let's assume that the curvature is always non-zero. Then you can build, well, the normal vector and the binormal vector, which is given by the cross product. And then these three vectors, t, n, and b, form an orthonormal system. And if you, yeah, so here's a picture, right? So if you follow it around the curve, they're always following the behavior of the curve. And this triple T, N, and B, which is, we think here as living in R9, they solve a certain kind of differential equation, y prime equals fy, which looks like this. So here the kappa here is the curvature, and there is another function tau, which appears here, which is called the torsion of gamma. And the torsion somehow measures how far this curve is away from lying in just in a plane. Yeah, so how much it goes out of a plane. Okay. All right, and there's this well-known theorem that conversely, if you're given such functions kappa and tau, and kappa is, let's say, always positive, And then there is an essentially unique C infinity curve gamma, parameterized by arc length, which has kappa as the curvature and tau as its torsion. Okay, and so here's our little application. Right? So now this was exactly a system of the type that I was talking about before, skew-symmetric matrix, and the n was odd. So if H is now maximal, and you assume that it contains the terms of kappa and tau, then the terms of this curve can be expressed. Well, they will all lie in this subvector space generated by cosine phi and sine phi and 1 over H. So this means you can explicitly describe this curve in terms of terms from H. And yeah, so simplest example is the helix, right, where kappa and tau are constant, and then what you get as the solution curve is the following thing here, right? And you see the sine and cosine pop up explicitly. Okay, so that's just a little fun example illustrating this theorem. So this was this parameterization of solution spaces that I mentioned at the beginning. So now I want to talk a little bit about differential operators. Now, if you have a basis for basis of solutions which is given by these exponentials, as in our case, then this essentially means that if you now pass to the point of view where you don't talk about systems of differential equations, but talk about scalar differential equations, or if you like, linear differential operators, then this tells you that this linear differential operator can be written as a composition of order 1 operators. So let's now take this point of view. So now I'm working in this ring H square brackets there. So this is the ring of linear differential operators under composition. Right, I mean, there's a commutation formula. Well, where's my chalk? There's a commutation formula for, it's fine, don't worry. Okay, so here's our differential operator. I assume it's monic, right? And the coefficients are supposed to be in H for the moment. Now, it's funny. So if you look at differential operators in this ring C less than infinity, there was actually a conjecture by Mamana who conjectured that if this operator has odd order, then it should have a monic factor of order 1. In general, this is false, as it turns out, but in the Hardy field world, it's true. So if now you take a maximal Hardy field extension of H, then indeed it is true that it factors into a product of order 1 and order 2 operators. So if its order is odd, it has to have an order 1 factor. Over the complexification, this statement simply means that over the complexification of E, A factors as a product of order 1 operators. Okay, and then you can say when A factors into a product just of order 1 operators. And this will be the case if and only if A has no oscillating zeros. No oscillating zeros. And this, well, I don't want to say much about this, but this is closely connected to the topic of disconjugacy. So this means also that A is eventually disconjugate for those of you who know what that means. Now, there's something interesting here that happens in part 2. In part 2, you can make this factorization unique in a certain way. So there's a certain requirement of the factorization, which I'm not going to write down, but that guarantees that you have a unique such factorization into order 1 operators. And this implies that, in fact, because of this uniqueness, the factorization happens not just over E, but already over a smaller H field, namely the intersection of all maximal Hardy fields that contain H. So this is this field E of H, which Bojanitsyn introduced. He called this the perfect hull of H, which is maybe not such a good term. And yeah, this one should maybe take with a grain of salt because we haven't written up all the details of this, but with a little bit, well, with some more work and some extra hypothesis on H, you can actually show that also in part 1, the factorization happens over E of H. Okay, so this is about the factorization. Well, we are model theorists, so we're interested in definable properties. Now, of course, these solutions, these exponential terms, they are oscillating. They don't live in a Hardy field. But still, you can say something about their properties in a definable way just by looking at the coefficients of the equation. So, yeah, okay, this is a very blanket statement. So many properties of the solutions of this operator are typically definable in terms of the coefficients. So let me make this a little bit, I give you one example where I make this precise. So for example, you can take, let's call them now B1 up to BR, polynomials over H in C1 up to Cm, and the C's are supposed to be for coefficients that are substitute, and the substitute constant coefficients. All right, so then for every m tuple C, I get a linear differential equation over, well, if R contains H, then this is just, if H contains R, then this is just H. So I get an equation L sub C. Okay, and then we saw before, right, so having no oscillating solution is connected to factoring into order 1 operators. And the set of all those parameters where you have no oscillating solution is a semi-algebraic set. And well, this uses, in fact, the quantifier elimination that I talked about before. And you check there that the induced structure on the constant field is just the ordered field structure, and then this follows once you know that you can express this in a definable way. And so, okay, and then of course you can take other properties, right? For example, having unbounded solutions or bounded solutions and whatnot. All right. Aha. And then, yes, the Cauchy-Euler equation. Let's see. Do we have time for that? Right. So do you remember how you solved the Cauchy-Euler equation? And let me rewrite it a little bit. Right. Let me write x squared y double prime plus cx y prime plus dy equals 0. You do a change of variables, right? You do c equals y composed with e to the x, and then you take derivatives of this, right? You get this, and c double prime e to the 2x plus e to the x, but this of course is just c prime, right? And then, well, you substitute e to the x into this equation, right? So get e to the 2x y double prime composed with e to the x plus c times e to the x y prime composed with e to the x plus d times y composed with e to the x equals 0, right? So this here, sorry, this whole thing here is c double prime minus c prime, and this here is c prime, and this is c, right? So you now end up with the equation c double prime plus c minus 1 times c prime plus d times c equals 0, and this has constant coefficients, and for equations with constant coefficients, we know how to write down the solution space, right? So now what you do is you look at, maybe I should call it c, so c squared, it's a characteristic polynomial, and it depends, well, this, you look at the zeros of this, let's call them lambda and mu, and now it depends on whether lambda and mu are the same or not, right? So if lambda is not equal to mu, then you get e to the lambda x, e to the mu x as the solution of this equation, but now you have to undo your substitution here. So you end up with x to the lambda, x to the mu as the solutions of the original equation. And if lambda is equal to mu, then you get e to the lambda x and x times e to the lambda x. And this means you get the solutions x to the lambda log x times x to the lambda. And now having non-zero oscillating solutions, well, now it's all about whether these lambda and mu are real or not, right? And this, of course, you can test by looking at the discriminant of this polynomial. And I hope I haven't made a mistake, and the sign is actually correct. Okay, right. Okay, now in fact, well, this technique of making these changes of variables like this, that plays an important role in our business. So this is not totally untypical. Okay, also in the constant coefficient case, we know how to solve equations. So now you can wonder, and this is a classical topic in ODE theory, what if you have a linear differential equation that's close to one with constant coefficients? So let's now assume that the A1 up to AR are bounded, meaning that they have a limit at plus infinity, which is a finite real number. But also let's allow these A's to be actually complex, okay, to make things a bit more interesting. So then we can form the characteristic polynomial, as I did in this example, right? But instead of just taking the coefficients outright, I need to take the standard parts. In other words, the limits at plus infinity. And well, then, you know, the general philosophy is that, yeah, you can read off from the zeros of this polynomial a lot about the solutions of the equation a of y equals 0. And in the Hardy-Field context, this also applies. So for example, if this characteristic polynomial has no real zeros, then there is no Hardy-Field extension where the equation a of y equals 0 has a solution in the complexification. So yeah, so now you can write down some very complicated linear differential equation. As long as it's of this type, right, the coefficients are all bounded. You look at the characteristic polynomial there. I'm not going to do it on the blackboard, but you can do it, and you factor it, and you see that there are no real zeros. So automatically you know that you cannot have a solution that is non-oscillating in a Hardy-Field. Okay. Another example of the same kind. Let's assume that the zeros of this characteristic polynomial are actually all simple zeros. So then there's a classical statement, I'll say a little bit about that, that this C-linear space of solutions then has a basis consisting of units, so the y1 up to are units in this ring, such that, well, well, if you take this for n equals 1, for example, this says that the logarithmic derivative of yj goes to cj, right? And well, it goes for this higher derivative, so y double prime over y goes to c squared, etc. But from our from our description of the solution spaces, you can actually see that, well, you can take these y's here in this context to be of this exponential nature as before.
What do you mean by complex functions? What is the order there?
Sorry?
Absolute value? I mean, what is this relation for complex functions?
This one?
Yeah.
Oh yeah, this is just, yeah, so yeah, you're right. I mean, these are now oscillating things. Yes, yeah, so this means just that the limit is 0 at plus infinity, yeah. Yeah, so the y's are oscillating, right? I mean, they are in the Hardy-Field setting. They are, as before, there's one term that is non-oscillating times an exponential that is oscillating. And this is, in fact, a strengthening of a theorem of Poincaré, who proved this, again, for holonomic functions. And then Perron proved a generalization later. But for some strange reason, they all assume that the real parts, they assume something stronger than the series to be simple. They assume that the real parts are all distinct. Now, in that case, we can say something more. Now, if the real parts are all distinct, and let's say I ordered them so that they're decreasing, then, in fact, there's a unique factorization of your differential operator into a product of order 1 operators, where all the factors take the limit given by this 0 at plus infinity. And again, because of uniqueness, this actually implies that this factorization happens already over this perfect hull of H, or its complexification. And we don't know actually whether we can relax this. I mean, whether this also holds if some of those real parts are the same. Yeah, and okay, this we can maybe skip, but there's a connection with these real parts to something called the Lyapunov exponents of these YJs, which is another topic in ODE theory. Okay. So now finally, in the last minutes, let me turn to the order 2 case, because this is interesting. So let's look at an order 2 linear differential equation. Now, if you have a non-zero, non-oscillating solution, then by Sturm's theorem, every solution is non-oscillating. And in that case, actually, you don't need all our business, because all these solutions will actually lie in a Hardy field outright, namely, again, in the perfect hull. So because there you can use the Riccati equation, solve the Riccati equation, which is an order 1 equation, and everything is fine. So the interesting case is, if you have an oscillating solution. And then the special case of our theorem proves a conjecture of Bouchard-Nitzan. So if you have an oscillating solution, then you can parameterize the solutions in the following way. So there are two terms, G and phi, in some Hardy field extension of H. I'm not assuming H maximal here, such that the solutions are precisely given by a constant times G times cosine of phi plus D for another constant D. Okay. And in fact, in some favorable situations, for example, if the value group of H has the smallest non-zero Archimedean class, then you can actually show that G and phi are unique up to constants, right? Of course, you can always multiply G, let's say, by some non-zero constant. And then again contained in this perfect hull. This is of course related to this factoring business over E of H that I talked about before. Right. So now a lot of differential equations that are used in the topic of special functions are actually of this type. I mean, this might look very simple, but equations of this type play a big role in mathematical physics. And I think the reason is that because a lot of the partial differential equations that come up in physics are of order 2. And then if you choose a certain system of coordinates, if you're lucky, you can do a separation of variables and transform it into an equation, an ODE of order 2. And then you end up with equations of this type, right? So there are lots of examples, like famous names, Legendre, Laguerre, etc., that are associated with equations of this shape. And one famous example is the Bessel equation. So we picked this just, I don't know, because it's the first one that came to mind, and we analyzed this a little bit and saw what our methods gave us in this case. Right, so this is the Bessel equation. So it's well known that it's oscillating for any value of this parameter nu. And in this case, we can actually strengthen our theorem. So there is a unique term in some Hardy field, which is close to X, such that you can parameterize the solutions in this form. Okay, this is really just a special case of the previous theorem, except for this uniqueness of this term. So now this term, of course, is now interesting, right? It actually turns out, again, as a special case of the previous theorem, that it lies in the perfect hull of Q, of the smallest Hardy field. So it lies in every maximal Hardy field. And only for very special values of nu is it, let's say, Liouvillean, so that you don't need our theorem. You can get it using easier tools, namely if it's a half integer. Okay, so let's see, how much time do you still have? 5 minutes, okay, good. Yeah, so then I don't need to rush. Right, so this is, this equivalence here is essentially a theorem that was already shown by Liouville. Liouville in here means that it's, contained in the Liouville closure. So you can close off under exponentiation, integration, logarithm, real closure, to obtain this phi. And all right, so this is a more precise result than the previously known expansion here. And it's a little bit curious that there's so much known about Bessel functions from the 19th century, but well, nobody thought about them in the context of Hardy fields. But knowing this fact, you can reprove a lot of basic things about Bessel functions or solutions of this Bessel equation without anything. I mean, so let me give you an example. So for example, we have an asymptotic expansion for this phase function. So these are the first few terms. Looks horrible. There's in fact an explicit formula for the nth term. And let me show you how, okay, there should be at least one proof, right, in every talk. Let me sketch you how the proof goes. So this, okay, so this phi satisfies a certain horrendous algebraic differential equation. But there's a miracle. If you look at 1 over phi prime, it satisfies a nice linear differential equation of order 3. And this is the equation. Okay. So yeah, this f here is this term that's cooked up. So the mu here is this 4 times nu squared. Nu was the parameter. And this psi here, in fact, well, because the phi was, remember, was asymptotic to x, so phi prime is asymptotic to 1, so the psi here is asymptotic to 1. Okay, so now you have this very explicit, very simple linear differential equation. You can go to the trend series and explicitly solve it. Okay, because trend series, remember, are formal series. You can just compute without thinking about convergence. So you can show that with not too much work, it's maybe a page of computations, that there's a unique solution of this equation with this asymptotic psi conditions in T, all right, namely the one that is on the right there. Okay, and then you just use the transfer theorem where you allow parameters from Rx to write everything down. And you can say, for every finite part of the asymptotic expansion, that there's this unique phi that has this beginning asymptotic expansion, and you just transfer it, level by level to the maximal Hardy fields containing phi. Okay, so there were some particular solutions of this Bessel equation which are very important, which are called the Bessel functions. So they're well, here I restricted them to the real positive half axis, but in fact that they extend to the complex plane minus the negative half axis on the reals holomorphically, and they're given by these the Bessel function of the first kind. This is the chain U. This is given by a certain power series expansion, and then the y nu is defined in terms of the chain U. It's a bit complicated because you first need to define it when the numerator doesn't, the denominator doesn't vanish, and then extend it by analytic continuation. But okay, yeah, here's a graph for the J's. So you can nicely see for J for nu equals 0 and 1 and 2, so you can see nicely the oscillation. Okay, and now what are so these are particular solutions, and well, now the question is how can they parameterize using our parameterizing schemes, right? So what are the coefficients C and D that you need, and well, this is how they turn out to be, right? So here is the here's the C somewhere hidden, and this is the D. And for the Bessel function of the second kind, there's a similar thing, but I've phrased it here in terms of sign. And yeah, this is the only point in the whole story where we need some complex analysis, because there is a classical asymptote for a classical asymptotic estimate for chain U, basically for the first term in this asymptotic expansion, which is due to Hankel and which uses some very simple contour integration to prove. But as a consequence, now once you know this, right? Once you know that you have this representation of chain U and y nu, and you know our asymptotic expansion for 1 over nu prime, which we had before, then if you just take the square of these two guys, add them together, and do the same thing for the asymptotic expansions, then you get in one line you get an asymptotic expansion for chain U squared plus y nu squared. And this result has an interesting history, So this was established by Nicholson in 1910 in a quite different way. And he used a sort of an integral representation of this function, j nu squared plus y nu squared, involving something that's called the modified Bessel functions. And this also involves some horrendous contour integration and deformations of contours. So in this classical book of Watson, this takes, I don't know, 10 pages. I mean, it's quite a long argument. And in this book of Olver on special functions, he sketches this argument and he says then, that it's difficult. But in our, with our tricks, this is, as I said, it's just immediate. So this is kind of nice. All right, and then,
You were
huh?
close to a negative number of minutes.
Yes, okay, so one more slide. Then the series of the Bessel functions have been studied extensively, so let's enumerate them. And then one result that we can prove in a similar way as before, namely using transfer from T, so first doing this whole thing over T, and then using a fact that Boucher-Nitzan proved, namely that this E of Q is closed under composition, you can actually parameterize the zeros of the Bessel function using a germ in a Hardy field, and then again you can, by first doing it over T, you can compute an asymptotic expansion for this nth zero, which is given here. And again, it looks pretty complicated. It was shown in the 19th century already by McMahon. And this is also amazing. I learned from Watson's book that for nu equals 1, this asymptotic expansion shows up in Gauss's notebooks in 1797. This is remarkable because this was decades before Bessel introduced the Bessel function. So and there's also an odd statement in Olver. I mean, he says, he gives this expansion, and he says no explicit formula is available for the general term. But, in our proof, because we do everything explicitly in T, you can compute a formula, right, for the general term. He does it differently, so he can only compute successively, the nth term if you have to, so by some substitution. But in our thing, this just falls out, so there's an explicit formula. Okay, I had more to say about this E of Q, but I'm sure somebody will ask a question about it, and then I can get to the next slides. Thank you.
So thank you so much for this beautiful talk. So, any questions? Okay, so first of all, what language did you say we have quantifier elimination in?
It's the language of valued ordered differential fields plus two certain convex subsets of the field.
I see. So even though there's such a huge definable closure, you don't need it explicitly.
No, yeah.
Another completely, probably, suppose you take definable type in R squared, like x goes to infinity and then y goes to infinity, lexicographic. And you look at fields of functions, or of germs of functions along that. Is it, so now it's presumably a differential field in PD differential field.
Yeah, right. I mean, that's a good question, right? So you're basically asking about a higher, a PDE version of this whole thing. Yeah.
It's half
I mean,
PD,
yes, yeah. So
it's half PD, but in some sense maybe you
right. You fix, the directions.
X and then
Yes.
y,
Yes.
so it's kind of
This would be interesting. Yes. Yeah. I mean, there's also a question about sequences, right? I mean, so we work here with germs of functions, but Boucher-Nitzan also developed the theory of Hardy fields of sequences. Yeah. So this because that's particularly interesting for this applications in ergodic theory. And yeah, I mean, that's another thing one could do.
Hi, Matthias. Do you know what E of Q is? Descriptions of E of Q?
What E of Q is? Okay. Well, the description. Let me show you the next slide.
How much money?
it's it's the intersection of all maximal Hardy fields. So if you're in E of Q, you're somehow unavoidable, right? I mean, if you want to, I think this is also interesting for O minimality, right? Because somehow, if you construct bigger and bigger O minimal structures, somehow, these. Right. I mean, it's known that it's differentially algebraic over the reals. This is shown by Boschanitsan. And we actually showed that it doesn't matter whether you take C infinity Hardy fields, maximal C infinity Hardy fields, or C omega Hardy fields. But it has a lot of closure properties. So let me just finish with this last slide. And I have a crazy speculation what this E of Q actually might be. Namely that it might actually be the Hardy field of the path enclosure of the reals. Maybe, yeah. I mean, because if you look at disclosure properties, it looks a lot like it, right? I mean, it's Liouville closed under Pfaffian functions, closed under composition. It's not known that it's closed under inversion, which is a bit funny. Well, it also looks as if it has something to do with, definable closure, because, somehow the way that, to show, whenever we show that something lives in this field, it's basically by showing that there's a unique solution of something in the maximal Hardy field, then it has to be there.
Okay. So maybe we have still time for a quick question, but Matthias is not allowed to show more slides.
So if we look at the Hardy field, the maximal Hardy field that can be realized as germ of definable function in O minimal structure, do we know that that is the model of this?
So you're saying you take you do the same procedure and you apply Zorn's lemma to Hardy fields that come from O minimal structure, or you take O minimal structures under inclusion, right, of the definable sets, and you take a maximal thing like this. I don't know.
Okay, so let's thank the speaker again.